Good afternoon, everybody. Hope you enjoyed your day yesterday, your snow day. Today, I was going to get into standard deviations, but I realized a couple of things. First thing, it's really important that we actually have a look at dispersion, sorry, can't speak, have dispersion of data, so how it's spread out. We talked a little bit about range the other day, and that is a measure of dispersion. So I want to talk a little bit more about that. And I also want to start introducing you to shape, because once we get into standard deviation, these things, so we've already talked about central tendency, we've talked about mean, median, and mode. Central tendency depends on mean, median, mode, shape of your data, and the spread. So we really want to look at all three of those things before we get into standard deviations, which will be next. So have a look at this. I'm just trying to make it a little bit bigger. So it says, how does the shape of the distribution influence the measures of central tendency? So what we're going to do here, we're going to look primarily at the shape of the different graphs. So if you look at these graphs right now that are in green, you can see that all three of them are, what did I just do? Sorry about that. All three of them, refer to retirement age. So they took a population of people and they determined how old they were when they retired. So depending on the group, and we're going to talk about what things could cause the changes that we see in these shapes, depending on the group that was sampled, we got different results. So the first graph that you see is right here, and this is what we would call a normal distribution. And if you actually look right below it, okay, that is normal distribution. So you can actually see that right there. Histogram has a normal distribution. We're going to spend more time talking about normal distributions than skewed data, but we will be talking about those as well. So it's important that you understand those as well. So if you look up here, it says that this data can be considered symmetrical. It's dispersed symmetrically, so evenly. That means that the mean, median, and mode are all going to fall in the middle of the data. So right around the middle, that's where we can expect to find the mean, median, and mode. Maybe just a couple of units away from each other. Maybe not exactly identical, but very, very close to each other. The next two diagrams that you see in the center and on the right, you can see that they don't have the same shape. Each one of them kind of has a tail. So the first one kind of has a tail going to the right, and then the second one has a tail that's kind of going to the left. And if you look, I should have put them in the other order. Hey, if you look at this one, it looks very much like the diagram that's right below it. We actually say that this one is skewed to the right. So when we find a histogram that is skewed to the right, we know that in this case, the mean is always greater than the median. And we're going to talk about in just a second, I'm going to have an example going back to retirement age that could influence this, why this would happen. The other one we have is what's said to be skewed to the left. So if it is skewed to the left, it means that the mean is less than the median. And again, we're going to figure out why this could happen. It has a lot to do with outliers. So we'll talk about that in just a second. So you are going to see histograms with these shapes. Again, we're going to talk about them some more. We're going to talk about especially this one. Oh, I meant that to be a pen, but highlighter works too. Because when we get into talking about standard deviations, this one plays a big role in some of the rules we're going to use. Okay, so let's look at an example that helps us explain why we could have one of the last two graphs that we see. Why would we have a graph that we say is skewed? So this is a great example right here, and it's related to retirement age. So in this one, it says, consider the retirement age data. We've got 54, 54, 54, 55, 56, 57, 57, 58, 58, 60, 60. So if you were to do the calculations on these, you would see that you've got a mode of 54, you've got a median of 57, and you've got a mean of 56. All right, so right below it, let's take a very, very similar data set. And if you look in the first sentence, it says that the only difference with this data set is that one of the values of 60 has been replaced with a value of 81. So you can see right here. So in this group, we had two values of 60 at the end. Right here, we have one value of 60 and one value of 81. Now, if you consider the value 81, that is much larger than the rest of the values in the group. So let's just think about this first group for a second. This first group would have a range, and if you remember what we talked about with range the other day, range, we always take the largest number, so the largest number is 60, and we subtract the smallest number, 54. So we have a range of 6. There's 6 numbers in the difference between the biggest and the smallest. Have a look at this group of numbers. The range would be much different. We're going to have 81 minus 54, right? So 81 minus 54 is 27. Much bigger range of values. So because 81 is so significantly larger compared to the rest of the numbers, we would call that number an outlier. And we talked about outliers on the very first day. So that very first set of notes I gave you, it does mention outliers, I think at the very bottom of the first page. And outliers really affect an average. They really affect a mean. So in this group of data, we actually see that we have the same median and mode. They have not changed. However, because of that value of 81, the mean has moved to 58.7. Before, it was 56.6. So that data has been skewed, right? So if the mean is greater than the median, which it would be in this case, it's going to be skewed to the right. Okay, so one piece of data, an outlier that's really different from the rest of them, can actually change the shape. So in the future, when you look at these different histograms, one of the things you should keep in mind is that what could be occurring if we see a graph like the second one or the third one is that we have an outlier or a couple of outliers, right? And that really throws things off. I would talk about this with students too when it's, I'm updating marks and maybe we start a new unit and I put a mark in for that unit and there's only one thing in that unit and that particular mark wasn't your best mark. It was really, really low. So until I get more things in for marks that belong to that unit, it can really skew the data because that one low mark could represent the entire percentage for that particular unit and your whole average seems to drop. It skews that data, okay? So one piece of data or a couple of pieces of data that are very dissimilar from the rest can really make the data look different and show a change in the central tendencies. All right. There is another example here as well, very similar to the one about retirement ages. So in this one, it says, without knowing how data is dispersed, measures of central tendency can be misleading. For example, a residential street with 20 homes on it having a mean value of $200,000 with a little variation from the mean would be very different from a street with the same mean, okay, but with 3 houses that have a value of $1 million and the other 17 being clustered around $60,000. So just think about that. If we had, so this second street, if we had those 20 houses and 17 of them, their value was clustered around $60,000. Those other 3 that were valued at 1 million, those would be total outliers. It would be so different and it would definitely skew your data. So it really is a big difference how we're getting the mean, right? So in our first example, if most of the houses actually lie around the center, if most of the houses are about $200,000, little less, little more, your mean is very, very accurate there. But the second example, if 17 of them are valued around 60,000 and 3 are valued at 1 million, that mean is not that accurate, right? $200,000 mean. Well, none of these 17 houses fall around $200,000 and none of these 3 $1 million houses do. So knowing how data is dispersed is really important for us to truly be able to understand what the mean and the median, more so the mean, represent. Okay, so that's really important. Measures of dispersion. So measures of dispersion, like this first graph right here, where all the data is very clustered together, we would say that this dispersion would have a value of 0. Sorry, not this one. If all the data was identical, sorry. So basically, if it was a uniform histogram, it would kind of look like a rectangle, actually. This one is a very normal distribution, as is this one, but they are spread out more. So it's evenly spread on both sides, but you can see that this one, everything is kind of grouped together more. It's grouped between 2.5 and 7.5, whereas in this one, everything is grouped between 1 and 9. So they're both normally dispersed, evenly dispersed, but this one is spread out wider. Okay, and so that would have a difference in how we interpret things. Here is a definition of range. So we did talk about range already. It is a way to actually look at dispersion. However, it is very, very sensitive to outliers. So it's not always the greatest measure of dispersion because it is so highly affected by outliers. If you go back to the question about the houses, right? Those 3 outliers, those 3 houses that are actually worth $1 million, they really affect the range in this one. All right, so that's it. Hopefully, when we start standard deviations and we look at some more graphs, this will help you. You have a worksheet to do, and there is one question that's actually going to talk about dispersion on the worksheet. So get that done today.